Okay, we're going to look at one more optimization problem here. So this one's about a soda can. Usual soda can holds 355 milliliters. 1 milliliter is 1 cubic centimeter. We want to treat the can as a perfect right circular cylinder, find the dimensions of the can that will contain the same volume, and minimize the surface area of the can. All right, so we've got a right circular cylinder here, so let's start with a picture of that. We want to find the dimensions of the can. So usually when we think about a cylinder, we think about the radius and the height of the cylinder as the dimensions of that. And we want it to contain the same volume, but minimize the surface area of the can. All right, so we know that this is an optimization problem because we're being asked to minimize something here. Maximize or minimize, those are optimization word problems. So we want to start by finding our objective function. That would be an equation for whatever it is we want to maximize or minimize. So what we want to minimize here is surface area of this can. All right, so this is one of those formulas you either know or you look up. We had a formula sheet for our class which had some of these formulas on it. For a circular cylinder, the surface area is going to be the surface area of the side, which if you unfold that is a rectangle. One dimension of the rectangle would be the circumference of the circle, 2 pi r. The other dimension of the rectangle would be the height here. So that gives the lateral surface area, the surface area of the side of the can, plus I've got a circle on the top and a circle on the bottom. So the area of a circle is pi r squared. We have 2 of those though, one on the top and one at the bottom. So you look this up or you figure it out. It's not hard to figure it out if you think about it in pieces in terms of circles and rectangles. But this is the surface area of a right circular cylinder. All right, that's our objective function. Our constraint is that we want to keep the volume 355 cubic centimeters or milliliters. So our constraint is about volume. 355 should be the volume. Volume of a cylinder is area of the base times the height. So the area of the base is pi r squared times the height. All right, so there's our constraint. On all of these problems, the next main step is going to be to solve your constraint for one of the variables so that you can substitute into the other equation. Again, there's an easier way and a harder way on this problem to do this. I might notice that substituting in for h and simplifying would be much easier than substituting in for r, 2 different places, and simplifying. So I'd like to substitute in for h. So I'm going to solve this constraint for h, so I can substitute in for that and have my whole equation in terms of r. Okay, so 355 divided by pi r squared equals h, and that's what we're going to substitute into our objective function so that we can get all in terms of r. Okay, so when I substitute that in, 2 pi r times my h okay, so then I want to simplify this. I'm going to be taking some derivatives and some other stuff, so I want to simplify this. I might notice that I have a pi that cancels, and I have one of the r's that cancels, leaving 1 r there. All right, so I'm going to write a cleaner version of this objective function here. S equals 2 times 355 is 710 over r plus 2 pi r squared. Or if I'm going to take derivatives, I might want to rewrite this first term as 710 times r to the negative 1. Okay, so 2 different versions there of my objective function that I'm going to be using for the rest of the problem here. All right, we want to think about feasible domain. So this time our objective function is in terms of r, so I want to think about feasible domain for r. Certainly, r should be greater than 0. If r is equal to 0, I don't have a height. If we think about what happens when we let h approach 0 and think about maximum values for r, we'll really see that r approaches infinity as h approaches 0. So this is it for our feasible domain restriction here. All right, and then we're ready for some critical points. Okay, so I need a derivative, and I want to think about where that derivative does not exist and is 0. So derivative s prime I'm going to use the derivative from this last form here. Bring down the exponent, negative 710 r to the negative 2 plus 4 pi r. Okay, so there's my derivative. We might notice that that derivative does not exist when r is equal to 0. R equals 0 was actually not in the domain of the original function, though, so that's not technically a critical point. So on this one, really thinking about finding the critical points that make sense in the problem, we're looking for where this derivative is equal to 0. Okay, so I have to do some algebra here to think about this. I might add 710 over r squared to both sides. Multiply through by r squared and divide through by 4 pi. So I'll get r cubed equals 710 over 4 pi. And then if I cube root both sides of that, I'll get r equals cube root of 710 over 4 pi. I might notice that 4 goes into 710 and reduce that if you want. I'm going to leave it like that for now, and I'll simplify at the end. All right, so that's my only critical point. I now need to test to determine whether that critical point gives me the location of a maximum, a minimum, or neither. So there's a lot of ways you can do that. I'm going to use the second derivative test, really. The first or the second derivative test would be appropriate here. I do not have a closed and bounded interval for my domain, so I wouldn't want to use that test for absolute extrema. But I'm going to use the second derivative test here. All right, so the second derivative, s double prime, just taking the derivative of this, so bring down the exponent. Negative 710 times negative 2 will be positive 1,420 r to the negative 3 plus 4 pi. And I'm not especially concerned about the actual value of this second derivative. What I am concerned about is whether this second derivative is positive or negative when I put in my r value. So my r value here, even though it's ugly, kind of irrational number here, it's a positive number. When I put that positive number in here and simplify that second derivative, we're going to get a positive second derivative. Our second derivative will be positive when I put this r value in here, which tells us that we are concave up on that region. So this critical point is the location of a local minimum. Right, and so looking back up here, we wanted to minimize the surface area of the can, so that's what we were after, a local minimum. All right, so we're ready to come back over here and maybe think about answering the question. Our r value was cube root of 710 over 4 pi. If I want to leave that in exact form, the best I maybe can do with simplifying is to notice that 2 goes into both 710 and 4 pi, unless you want to rationalize the denominator. 355 over 2 pi. In exact form, that would be centimeters. It's our exact form answer for r. And then our h, I want to go to where I have a relationship between r and h, and I can use that to figure out my h value. I'm going to just leave it in kind of an unsimplified form for now. Pi times my r value squared. All right, if you want to do some algebra and some housekeeping on that, you can. I'm going to just leave it like that. When you do the homework online, it's okay if you type in an unsimplified answer. When you do it for me, I'm really more interested in the calculus here than in the simplifying the numbers at the end. But if you want to simplify it, you can do that. Also, you may be interested in some decimal approximations. The radius is approximately 3.84 centimeters, and the height is approximately 7.67 centimeters. All right, so we've done another optimization problem. This one was fairly complicated. Variables, derivatives, negative exponents, but they really all turn out about the same. So if you can get through one like this, you can probably get through most of the problems. I will post some other examples in our course shell that are written out, but really all the same kind of structure. So make sure you practice lots.